Welcome to Tech for Novice, your channel dedicated to technology for people without technical background. The first fatal accident of Boeing's 787 Dreamliner is Air India Flight 171 from Ahmedabad to Gatwick. This video explores probable causes of the crash based on available information so far, including basic technical information on the related aircraft system. Aircraft Accident Investigation Bureau of India released a preliminary report after about a month of the June 12, 2025 accident. The doomed plane was 12-year-old Boeing 787-8 Dreamliner with GE engines. This twin-engine aircraft had flown 41,868 hours before the crash. Only one passenger survived among 242 people on board. 19 people died on the ground and 67 more people were injured. V1 is the speed after which takeoff can't be aborted, mainly due to not possible to halt the plane before the end of the runway. VR is rotation speed to start liftoff procedure. V speeds are calculated for each flight based on aircraft type, takeoff weight, runway length, environmental conditions, and aircraft performance data. The aircraft reached V1 speed of about 283.36 kilometers per hour at 8 hours 8 minutes and 33 seconds and VR speed of about 287.06 kilometers per hour at 8 hours 8 minutes and 35 seconds. After 3 seconds of liftoff at 8 hours 8 minutes and 39 seconds, it reached highest speed of 333.36 kilometers per hour. Around the same time, both fuel switches were transitioned to cut off one after the other within 1 second. One pilot asked another pilot why did he cut off, and reply was he didn't do so. At 8 hours 8 minutes and 47 seconds, both engines lost power and RAT hydraulic pump began supplying hydraulic power. It was 8 seconds after liftoff. 10 seconds after cutoff, Engine 1 fuel control switch was transitioned to run at 8 hours 8 minutes and 52 seconds. 13 seconds after cutoff, Engine 2 fuel control switch was transitioned to run at 8 hours 8 minutes and 56 seconds. Engine 1 started recovery, but Engine 2 was still repeatedly trying to relight. Mayday call was issued at 8 hours 9 minutes and 5 seconds, and flight recorder continued to record 6 seconds more until 8 hours 9 minutes and 11 seconds, the final moment. Total airborne time was 32 seconds. Preliminary report says RAM Air Turbine was deployed during the initial climb immediately after liftoff. Both engine fuel control switches were transitioned from run to cutoff within 4 seconds of liftoff, causing simultaneous dual-engine flameout just after takeoff. Engine 1 relight occurred within 10 seconds after cutoff, but low altitude made recovery impossible. No recommended actions were issued to operators and manufacturers of B787 aircraft and GE engines. According to preliminary report, Engine 1 fuel control switch was transitioned to cutoff 3 seconds after liftoff. Engine 2 fuel control switch was also transitioned to cutoff within 1 second after Engine 1. However, it is not clear if the fuel control switches physically moved to cutoff. Most likely reasons for dual engine failure are fuel contamination, fuel starvation, bird strike, volcanic ash, ingestion of hail or rain. Human errors such as shutting down the wrong engine instead of faulty one and manual fuel cutoff for both engines could also be reasons for dual engine failure. AI171 B787 dual engine failure was due to fuel starvation, and other reasons are ruled out for now. Simultaneous dual engine failure is nearly impossible, yet it seems the most likely cause. Many people and media believe captain is responsible for deliberate fuel cutoff to both engines. The Indian probe body Aircraft Accident Investigation Bureau says it is too early to come to conclusions. Media report is basically based on 2 sentences in the preliminary report mentioning one pilot had asked the other why did he cut off fuel supply to the engines, and reply from the other pilot was he didn't. Both pilots were busy with the takeoff, and therefore pilot flying could have noticed fuel cutoff from flight management system display rather than looking at the switches. Was the cutoff deliberate attempt to crash the aircraft according to media report? If it was, then why did they try to relight the engines? If pilot monitoring did the cutoff intentionally, then he could have stopped pilot flying to restart the engines to ensure the crash. But there was no sign of scuffle according to the preliminary report. Let's explore technical aspects. Every commercial aircraft has electronic recording device commonly known as black box for helping post-accident investigations. These devices are designed to withstand extreme forces and temperatures, ensuring the data remains intact even after a crash. Two types of black boxes are installed in passenger aircrafts. One is Flight Data Recorder or FDR for recording a wide range of parameters, including engine performance, altitude, airspeed, vertical acceleration, control surface positions, and flight path data of last 25 hours of flights. Second one is Cockpit Voice Recorder or CVR for recording sounds within the cockpit, including crew communications, radio communications, and audible alarms during the last 2 hours of flights. B787 uses two similar enhanced Airborne Flight Recorders or EAFR which combine FDR and CVR in a single unit. They are installed at tail and forward sections. Fuel control switches are used to start or shut down engines on the ground. They remain at run position while airborne. When fuel control switch is moved from cutoff to run, it signals FADEC or full authority digital engine control to manage engine start. They are also used to shut down or restart engines during flight in case of emergency such as engine fire and flameout. Fuel control switches are designed to stay at run or cutoff position without pilot intervention. B787 fuel control switch is held in position by spring and seems not possible to shift position automatically or with remote commands. Changing switch position typically involves two deliberate actions per switch. First, it should be lifted 2.28 mm upward to disengage the locking mechanism. Then should rotate from run to cutoff or vice versa. Let's see how the switches are operated. US FAA had issued advisory on potential disengagement of the fuel control switch locking feature in December 2018. Fuel control switches transitioned from run to cutoff position means fuel supply was cut off. It could be done with physical movement of the switches or with system commands. If the switches were physically moved to cutoff, then the pilots should have done manually. It could be deliberate attempt to crash the aircraft by a pilot with mental health issues or inadvertent action by one of the pilots. Assuming it was deliberate action by a pilot, question remains how both switches were moved to cutoff within 1 second. Several pilots and experts say it should take at least 2 seconds. Another possibility is damaged switches by sabotage. However, it is still not plausible for both switches moving themselves to cut off almost simultaneously. If the pilots did not move the fuel control switches, then fuel control valves could have been closed by automatic commands from the system and recorded as fuel control switch transitions. Flight recorder records signals from the switches, not the switch movements. Software logic, not just physical inputs, determines how these valves operate during normal and emergency scenarios. More data analysis should be able to pinpoint the sources of the commands to close the fuel control valves. We need to dig in FADEC or full authority digital engine control to understand how the engines are managed. FADEC is a digital engine control system coupled with sensors and actuators which is capable of controlling the complete engine independently to provide optimum engine performance. It controls complete sequence of ignition, starting and shutdown of the engine and continuously monitors and adjusts engine parameters based on various inputs from sensors and pilot maneuver. Sensors inputs include air temperature, altitude, throttle position, engine temperatures and pressures, engine and propeller RPM, fuel flow, electrical system voltage, and a lot more. It also offers real-time diagnostics and self-correction capabilities, allowing pilots to focus on other essential aspects of flight without constantly monitoring engine parameters. Electronic Engine Control, or EEC, also called Engine Control Unit, or ECU, is an electronic computer system which performs all the computation in the FADEC system. Inputs received by EEC are analyzed up to 70 times per second. Main job of the FADEC is to protect the aircraft from pilot errors by validating inputs from various sensors and cockpit and taking full control of engine operation. FADEC is supposed to ignore pilot maneuver to close fuel control valves while still airborne, and no indication of anomaly. Sensors collect data of various operating conditions of the aircraft in real time, and actuators control various components by driving them after receiving commands from Engine Control Unit or ECU in case of engine operation. ECU is a component of FADEC. ECU analyzes sensors data and cockpit control signals to calculate optimum engine operating parameters such as fuel flow, stator vane position, air bleed valve position, etc. Computed optimum engine operating parameters are applied as appropriate using actuators after FADEC makes the decision. When fuel control switch is moved from cutoff to run, it opens Spar fuel valve, arms engine fuel valve, and selected igniters and signals FADEC to manage engine start. For in-flight starts, FADEC continuously tries to start the engine until successful or fuel control switch is moved to cutoff. When fuel control switch is moved from run to cutoff, it cuts fuel and power to the engine while on the ground or during emergency, such as engine fire. EC opens engine fuel valve and controls fuel metering unit to adjust fuel flow to meet thrust requirements. RAM Air Turbine or RAT is a small, wind-powered emergency turbine that deploys only under specific conditions such as dual engine failure, electrical failure, or all three hydraulic systems failures. It generates power through the airstream, which is dependent on the speed of the aircraft. It provides emergency power for vital flight systems and controls, linked hydraulics, and other critical flight instrumentation required to land the aircraft safely during loss of primary and auxiliary power sources. RAT will not deploy while the aircraft is still on the ground. B787 RAT is connected to central hydraulic system powered by two electrical pumps. Left and right hydraulic systems are powered by engine-driven pumps. RAT is deployed as soon as low pressure is detected in all three hydraulic systems, which can happen during a major electrical system failure or dual engine failure. RAT hydraulic pump of doomed B787 began supplying hydraulic power at around 8 hours 8 minutes and 47 seconds, around the same time as power loss from both engines. As it takes time to build pressure, RAT should have deployed before both engine failures at 8 hours 8 minutes and 47 seconds. RAT deployment time is crucial to determine the faults triggering it, but preliminary report did not disclose it. We can estimate RAT deployment time based on time it began to supply power. Dropping exhaust gas temperature, or EGT, is the first sign of engine failure, as lower power generation also means lower heat generation. Aircraft senses engine failure after 2 to 3 seconds of EGT start dropping. It is also time engine is spooling halfway down until when generator keeps producing electricity. RAT takes 4 to 8 seconds to build sufficient hydraulic pressure depending on residual pressure, according to some experts. It means both engines had already failed at least 4 to 8 seconds earlier than 8 hours 8 minutes and 47 seconds. Time both engines lost power. If this assumption is correct, then both engines should have failed somewhere between 8 hours 8 minutes and 39 seconds to 8 hours 8 minutes and 43 seconds. If the engines had failed before fuel cutoff time 8 hours 8 minutes and 42 seconds, then probable failure should be hydraulic or electric or both. Fuel cutoff time to both engines was 8 hours 8 minutes and 42 seconds to 8 hours 8 minutes and 43 seconds as recorded by flight recorder. If the system received erroneous data such as high pressure or fuel leak signals from faulty sensors, then system could have sent commands to close fuel control valve without human intervention. Another possibility is software glitch or logic fault or memory fault. In engine control unit issued an unintended command to stop fuel flow, though no fault existed. Flight recorder recorded fuel cutoff as fuel control switch transitioned to cutoff, though both switches remained at run position after fuel was cut off. Further investigation on flight recorder data should reveal the sources of signals to stop fuel flow. Engine 1 fuel control switch was transitioned to run at 8 hours 8 minutes and 52 seconds, indicates one of the pilots tried to relight the engine. Normal procedure to relight after flameout is to move the switch from run to cutoff and then back to run. It is obvious that flight recorder didn't record signals from the switch when it was moved from run to cutoff, as it was already at off position logically. Could be the reason for recorded 10 seconds gap between cutoff and run instead of normal less than couple of seconds. Signal from the switch movement form cutoff to run was correctly recorded as transition to run. Same things happened to engine 2. Fuel control switch was transitioned to run 13 seconds after cutoff. Again, it was normal relighting sequence. The switch was first moved from run to cutoff, but flight recorder did not record this change as there was no logical change. The switch was already at logical off position after fuel cutoff command. Flight recorder recorded only the signals related to the switch movement from cutoff to run, skipping run to cutoff 13 seconds after fuel supply was cut off, which should have taken about 1 second. Engine 1 started to show sign of recovery at 8 hours 8 minutes and 56 seconds, which was 9 seconds after losing power and 4 seconds after relight attempt. It takes 8 to 10 seconds to gain full power and few more seconds to reverse altitude loss. Engine 2 was repeatedly trying to restart but did not recover before the final moment. It is not clear why the pilots didn't try to relight the engines earlier. Maybe they had to prioritize other emergency before relighting the engines or lost few seconds in the panic. Seems pilots had tried their best to save the aircraft, but low altitude made recovery impossible. Was there any chance of success if the pilots had acted earlier to relight the engines? Seems unlikely. Another B-787 of an All Nippon Airways had fuel switches automatically transitioned to cutoff in 2019. The aircraft was approaching to land but mistakenly interpreted that it was already on the ground and cut off fuel supply prematurely to the engines without any pilot input. It was a serious software glitch, but the aircraft was able to land safely as it was already approaching the runway to land. The doomed aircraft had arrived Ahmedabad from Delhi before flying to Gatwick. The pilot flying the aircraft had noted in the technical log that it had a stabilizer position transducer defect, which was checked and troubleshooted by a maintenance team, according to Indian media. A stabilizer position transducer defect refers to a malfunctioning sensor that measures the position of the aircraft's horizontal stabilizer, a crucial control surface that helps maintain pitch stability. It is a critical issue as it can trigger incorrect responses in flight control, including uncommanded fuel cutoff signal, according to some experts. The aircraft also had previous false fuel system warning that flashed on control panel screen and electrical fault that led to the cancellation of a flight. Preliminary data hints at engine power loss, possibly due to fuel starvation or software miscommunication with engine components. Given the B-787's reliance on digital systems, the theory of a software-induced shutdown is now being closely examined along with maintenance records, pilots' medical records, and potential pilot errors. Please share your opinion on the cause of the accident based on the information available so far. Generally, we can divide reasons for the crash in 3 groups: pilot error, pilot's deliberate attempt to crash, and technical faults. Thank you so much for watching. If you liked this video, please comment, share, thumbs up, subscribe, and press the bell icon.